So welcome everybody to the Dublin Institute for Advanced Studies. My name is Tom Ray, and I'm director of the School of Cosmic Physics. There's a couple of housekeeping notices that I should give you all before we start. The first thing is fire safety. So in the unlikely event of a fire, as they say, we'll head out those doors, down the stairs and across the road. All right. Toilets, there's male and female toilets can be found on the ground floor, non-binary toilets upstairs on the 4th floor. So an overview of Samhain agus Science. So it's a Halloween inspired festival. It's an annual festival that we've had now for 5 years. And it's inspired really by researchers at the Dublin Institute for Advanced Studies, not just people in the School of Cosmic Physics, my own school, but also in theoretical physics as well, and in addition, Celtic studies. So quite a mixture of talks over the week. So it runs until the 7th of November, and there are more details can be got at our website. Now this evening, it's my pleasure to introduce a talk by Dr. Donna Rodgers-Lee. So Donna started off in the Dublin Institute for Advanced Studies, did her PhD there, went over to the UK, to the University of Hertfordshire for a number of years, and then returned to Trinity College first, and is now an SFI, Science Foundation Ireland, Irish Research Council Pathways Fellow in the Dublin Institute for Advanced Studies. And Donna's subject is cosmic rays and how cosmic rays interact with atmospheres of planets, not just our own planet, but planets, exoplanets. As you probably know, we now know of thousands of exoplanets around other stars. Basically, 50% of the stars that you see in the sky have a planetary system around them. And so conditions are very, very different in those stars from our own sun. And we're very interested in trying to understand the processes that go on on these exoplanets. So cosmic rays have been known for over 100 years now, and certainly in the past 20 years or so, we really have a good idea of where most of them come from. But what's particularly a topic that's being researched currently is how those cosmic rays, both from outside the stellar system and also the star itself, can affect planets around other stars, how they can affect the chemistry in particular, but also how they might affect life itself. So Donna is going to talk to you this evening. I think it's a great title. Brings you back to Ghostbusters. Slimer, not Slimmer, Slimer, or X-Men Mutants. So how energetic particles can affect life, in other words. So thank you very much, Donna, and I'll hand over to you.
Great. Thanks, Tom, for the intro. Great. Yep, so as Tom said, I'm going to talk to you about how energetic particles can affect life on other worlds. So as Tom said, I actually did my PhD here in Dias with Tom. But before that, I did an undergraduate degree in theoretical physics at Trinity. And then I went after my PhD, as Tom said, I went to Hertfordshire, then to Trinity and back to Dias. So I mainly work on, I'm an astrophysicist. So I just thought I'd show you kind of like the path that one might take to end up working on exoplanets in other systems. So this is, as I said, the main kind of question in my talk is, what do we think life would look like on other planets? Is it something like Slimer, which is an ectoplasm, so a very basic kind of life form, or is it something more advanced than what we have here on Earth, such as an X-Men mutant? And how do cosmic rays affect life on these planets, and are they more likely to cause one or the other of these two scenarios? And as also, as Tom mentioned, the first exoplanet was discovered in the 90s with 51 Peg B. And this was, so maybe, you know, before we knew there were thousands of exoplanets, we really just had this one in the 1990s. It's a hot Jupiter, which means it orbits very close to its host star. And this was the first exoplanet detected around a sun-like star, and was won the Nobel Prize a few years ago. But this is actually a very unexpected type of planet for them to have discovered. And people didn't think that exoplanets would be so big as like Jupiter would be able to orbit so close to the planet. And how this would have formed was a mystery. And so I suppose, you know, there's been a lot of progress in the last couple of decades, but there's, you know, constantly new discoveries which really challenge how we think about these systems and what sort of systems are like or are likely to occur. So this was the first exoplanet, and it was a shock, wasn't expected. And so since then, lots of progress has been made on detecting other exoplanets. And there's two main types of ways that we would detect exoplanets. The one on the left is kind of like to do with the star wobbling. So the star and the planet, you think of the Earth orbiting around the sun, but really the sun and the Earth orbit around each other. And so if there's a planet that we can't see because it's too faint, but we can see the star, we can detect the fact that it's wobbling slightly due to the gravity of the planet. So this is one it's an indirect method, I suppose, as we can't see the planet itself, but this method has been used to detect thousands of exoplanets. And then the one on the right is called the transit method, or this is basically when the star blinks. And so if we stare at the star, it's like a light bulb, and if something passes in front of your light bulb, the light bulb gets slightly dimmer. And so when the planet moves and transits in front of the star, we can see the starlight dim slightly, and we can detect this. It's a really small amount of light that gets dimmer, but we can detect this. So this is another method that's been used again to discover thousands of exoplanets. I suppose for the transit method, the planet has to go in front of the star. So if it's orbiting like this in the plane of the sky, we won't be detecting those sorts of planets with the transit method. So there's lots of dedicated missions now that look at the sky to detect thousands of exoplanets. So this is one of the Kepler sort of overview of planet systems. So in the center, you can see the solar system, and then all the other circles, it's not showing up very well on the screen, but there's sort of circles to show the orbits of all the planets, and the size of the symbol shows the size of the planets. So we discover things like Mercury all the way up to Jupiter's. And then some of them are really, the color is how hot they are. So we're discovering really hot planets like hot Jupiters, which are thousands of Kelvin or degrees hot. So much, much hotter than the Earth. And some of them are very far away and some of them are very close in. And so we had this huge variety. And this is quite like remarkable, really, because if you think about it in the 1990s, you know, whether or not there was life somewhere else in the universe depended on how many planets you had in the galaxy. So if we didn't know there were other planets, then there wasn't, you know, it was hard to think about where life would form. So it's really quite like revolutionary that we now know that there are thousands of planets in the galaxy. Practically every star, as Tom said, should have or is thought to have a planet. And therefore, of all these planets, we start to think about which ones might have life on them. But this is obviously really good news that there's planets around most stars like the sun, because then we think that there should, well, I think that there should be life somewhere else in the galaxy, because it seems like, well, I mean, I suppose we could be a lucky chance, but the odds are good, I suppose, if we have so many exoplanets. So the first thing that people, the first sort of criteria that we think of that is necessary for life to exist on another planet outside of the solar system is that there would be liquid water on the surface of the planet. And so this, there's like a zone which is called the habitable zone. And this is the distance from a star where liquid water or water can be liquid. So if you are too far away from your star, like Pluto, you have ice and it's too cold. And if you are too close to the star, then you have vapor or steam, which JWST has detected. So you'll have a steamy atmosphere, and neither of these are very good for life. So people have come up with the idea that, you know, you need liquid water. And so this is the kind of green region here. So there's different types of stars. Some stars are much hotter, and so the habitable zones for those stars will be further from the star than it is for the solar system. And then there are cooler planets, which are red. So basically, as you change the temperature of your planet, it gets, sorry, of the star, it's like turning up a light bulb, so they get brighter, but they also change color slightly. So as you go down, you get these cooler stars, which are called red dwarfs. And so you need to be orbiting really close to the star there if you want to have liquid water on the surface of a planet. And so that's what I've just shown here, that the color of the star itself also changes, not just how bright it is. So I'll just mention TRAPPIST-1. This is a very famous system, very hot topic in astrophysics. This is a system, it's a red system of exoplanets that's being detected around a young red dwarf star. And there are 7 rocky planets that they've discovered, and they all orbit within the orbit of Mercury in terms of the scale in comparison to the solar system. And this is one of the targets for the James Webb Space Telescope. Some of these planets orbit also in the habitable zone. I think there's only 3 or 4 systems we know of where there's a kind of Earth-like analog in the habitable zone. So we get plenty of hot Jupiters, but we don't really think that life is going to happen on hot Jupiters, which I'll explain in a few more slides. So this is one of the really top candidates for detecting life or the signature of life on an exoplanet outside of the solar system. And if you'll see here as well, actually, the green region is the habitable zone for the solar system, and Mars is within the habitable zone of the solar system. And Venus is kind of just on the edge as well. So you kind of see that even in our solar system, this criteria isn't perfect because Mars doesn't have any life on it at the moment. It has no liquid water and has no atmosphere. So it's not a great place to live. And so, yeah, no, except for Elon Musk, who thinks that. So you can see how this is it's like a rough guide. It's where we start. So the first criteria is whether you can have liquid water. And this is actually kind of an analogy for my work, is that I like to think of, we want to come up with the range of distances from a star, or the age of the star, where it's okay to live there in terms of how many cosmic rays you're hit with. So these are another condition for life. If you have too many of them, they're going to be bad for you, and you have too little, maybe life won't start in your exoplanet. And so it's just come up with a similar kind of system of distances from a star where life could exist. And I'll also discuss actually as well the age of the star, because this is for the current sun, and maybe at different times during the sun's history, it would not have been, Earth would not have been as habitable. So as I mentioned there, liquid water is one of the top criteria when we think of looking for life as we know it on another exoplanet. But this is just a terrible mess of words, which shows you how many different other things people think about in astrophysics other than liquid water in relation to the habitability of a planet. So, so there's stuff to do with the planet itself, like whether it's got clouds and hazes, because that affects how hot the planet is, kind of like the greenhouse gas effect, and the temperature of the planet. Whether you actually have an atmosphere, again, Mars has no atmosphere, so that's why it's not so habitable today. So the atmosphere can be lost during the evolution of the planet with time. You have the star itself, what age the star is, whether it's very active or where it's kind of quiet, like the sun is at the moment. Where the star is in the galaxy, is it close to the galactic center where maybe things are a bit, more unfavorable, or if you're close to other stars, either you have, other planets which kind of interact. So there's really a large number of things that people are thinking about at the moment when they're searching for these, when we're trying to come up with a list of habitable planets to look at with our future telescopes. So the two sort of topics that I look at are up there on the left. So I look at the sort of magnetic fields of stars, the winds that those drive, so that all ties into the age of the star. And then also cosmic rays, which is possibly linked to the origin in the galaxy, or the birth of the exoplanet within the galaxy as well. And one thing which is just kind of an aside, which I think is quite nice to think about as well, is that, for these the red dwarf systems where you orbit very close to the star so that you can have liquid, we think the planets might be habitable where there's liquid water, but then you get into this regime of where you're so close to your star that you'll be tidally locked. And this is, if you don't know what that means, that's what we have for the moon. So the moon is tidally locked to Earth. And that's why we always see the same side of the moon. So even though the Earth rotates, the moon also rotates. And so we always see this on the left-hand side. This is what we see from the moon. And it actually looks very different from the back because it got hit by a load of asteroids on one side, but it didn't on the other because the Earth was facing it. So this is what it means to be tidally locked. You always see the same side of a moon or a planet. And so planets can be tidally locked with their star. And that means one side of the planet is facing a very hot object, and then the back of the star or the back of the planet isn't. And so that means you expect these very strong like winds around the planet because one side's very hot and one side's very cold. And that causes an extra kind of complication for whether you think life could exist on a planet like that has only got, it's going to have ice basically possibly on one side of the planet and then, you know, steam or water on the other side. So you've kind of got a competition there between gravity and sort of heat effects. So I've mentioned liquid water as some of the conditions that we think would be required for life as we know it. So this is kind of why when we're thinking about life, we kind of often start with life as we know it because there's too many unknowns if we start thinking about life as we don't know it. So we can kind of focus on life on Earth and then how that can inform us about life or where life on Earth might survive elsewhere on another exoplanet. Or we can also be a bit more exotic and think about like, well, okay, fine, if you've got like a gas giant planet like Jupiter, is it possible that something might live there in the clouds? And so I've mentioned liquid water, but you also it's good to have a solid surface. And so that's why people focus on like a rocky planet like Earth. And that's because that gives you kind of a surface where you can maybe have a pool. And that means you can do stuff in the pool with chemistry. So you can form a little, it's like a little warm little pond. If you have an ocean or a gas giant, which is basically, you know, a big circulation system, things move around too much. And so it seems to be quite hard to come up with a way of how life would form in something that's moving too fast. So you kind of need something a bit steady, like a lake or something like that. And that's why it seems to be important to have a solid surface. And then a lot of people do seem to think that it's going to be a carbon-based life form, which is like us on Earth. And that's because carbon is one of the most abundant elements in the atmosphere. And so, yeah, these are some of the things that people think about when they're thinking about where life, the type of life that might exist. And this is a picture from the International Space Station, because I suppose what they do there as well is figure out could life have started not on Earth and could it have been delivered to Earth? So one of the things they want to know is if you put bacteria in space or little lichen in space, the poor things, do they survive? So they stick them to the outside of the International Space Station and see how they cope with living in the vacuum. And they actually do quite well. So it seems like you could deliver life to Earth. So it doesn't necessarily have to have been started on Earth itself, possibly just somewhere else in the solar system, probably not from outside. That's quite a long journey. Yeah, so these are some of the, again, more of the things that people are thinking about. Oh yeah, and as I mentioned here, this is kind of this asteroid kind of scenario for how life might have started. So you have these things called prebiotic molecules, which are shown kind of here. They're just, very basic molecules, but they are thought to be very important for the origin of life because they go into things like DNA. So this one here is actually was detected in 2016. So a telescope looked for the signature of this molecule from another region far away that has stars forming, and they detected PO, which is a phosphorus compound, and this goes directly into the DNA structure. HCN as well is another one of these molecules that which hydrogen cyanide, and that's another one that goes into the DNA structure. So these are the little building blocks that we think are required to start life on Earth. And cosmic rays or energetic particles can actually contribute to the formation of compounds such as HCN. So if you can kind of form them in space, then maybe you could deliver them to Earth. So that's one of the ways that people think that life might have started on Earth. And that's why they're looking for these molecules in different regions of space to see, like, is it very likely? Because do these compounds, these chemical compounds already exist in space, which they do. So that's good. So back to the cosmic rays, as Tom mentioned, this is what I was supposed to be talking about. So what are cosmic rays? They were discovered in 1911 by a man called Victor Hess, who went up in a balloon, a very novel science experiment. And he basically, he thought that they were counting the number of particles, or the number of ions that were produced. And he thought before he did the experiment that as you went up in the atmosphere, there would be less of them, because he thought they came from, like, you know, the center of the Earth, kind of like a radioactive core or something. Something was happening in the Earth's mantle that was causing these particles to kind of come up. But it actually turned out that they were coming in. So when he went up into the atmosphere, this number went up with height. And this is when we discovered that there are these very high energy particles that come from space. So they're protons. They're just one of the atoms, or not the sorry, one of the particles that make up all the atoms. And they're traveling very, very fast and very close to the speed of light, as they're relativistic particles. And they can travel, you know, great distances through the whole galaxy. And then they hit the atmosphere of an exoplanet and kind of lead to the wealth of chemistry that's observed. So this is the second and only kind of graphy plot that I have. So this is basically nowadays a kind of modern picture of the picture that, or of the graph that he had. So you have the number of these cosmic rays which come from the galaxy and their energy. And I just like, you know, because it's not a competition, but this is CERN, the particle accelerator, and it can go up to this number here, which is very, very large, 10 to the 12. And then these cosmic rays go all the way up to 10 to the 20, so that's a billion times or more than a billion times more energetic. So the universe is really good at accelerating particles. Anything that up to here, we detect, in this region, we detect 1 particle per square meter per year. So it's quite a long wait when you're doing these, when you're looking for these particles. And when you go to the even higher energies, we only detect 1 of these particles per square kilometer per year. And so we use like the ice I actually don't know if it's the North or South Pole, but they use the ice to detect these particles. So there's really very few of them. But the ones that are kind of intermediate energy here, they come from our own galaxy. And they come from when they're accelerated when massive stars explode. Or not massive stars, sorry, when a star dies, some of them are massive enough to explode in a supernova. And when they explode, the particles are accelerated around them. And then these particles travel to the galaxy and hit us. If they're higher in energy, they come from outside of our galaxy, so they're extragalactic, and they might come from the center of a galaxy, so the very, very center where the black hole is, and it's really, you know, accelerating a lot of particles there as well. Anything that's very low energy down here is actually affected by the solar wind and is suppressed. So I'll explain what the solar wind is in a second. So obviously we have loads of detections of these particles now, and we know vaguely the 3 different categories of where they come from. So the good news is that the solar wind protects us from the galaxy, and this is kind of a cartoon of what the solar wind kind of does around the Earth. So this is the sun in the center, and the sun has a wind, a really hot wind that pushes out all the material away from us. And so this is the interstellar medium, or the area outside of the solar system here on the outside. And basically the cosmic rays find it quite difficult to come in through this wind. And so they're kind of suppressed, and we detect less of them than you would if you were in the interstellar medium. And the reason we know this is actually because we sent 2 probes out into the interstellar medium 50 years ago, and they're still operating, still sending back data that's used. And in maybe 2012 or 13, I can't remember the exact date, but they crossed this barrier, and they finally reached like interstellar space. They're no longer in the solar system, they're outside the solar system. And then the number of cosmic rays went up. So you could really detect that the solar wind is protecting us from the galaxy. So this is really remarkable. I mean, they still run on like tapes, I think. It's pretty impressive to see something 30 years or 50 years on sending back data. And I mean, it takes a while for the data to reach us because, the speed of the information, it takes, not seconds, it takes like 24 hours, I think, for the data to reach us. So that is pretty cool. Good hardware, I suppose, good engineers. Yeah. That's the one that has the, the information, like if an alien finds it, like what we're interested, or like, the pictures of people and stuff on it. That's the cool instrument. And so this is what we know about the sun and the solar wind. So if we want to know about other exoplanets, we need to know about there's the equivalent of the solar wind. So do they have the same kind of winds? Are they stronger? Are they weaker? So do they have more cosmic rays or less cosmic rays? So just kind of to situate you, sorry, go to the next slide. To situate us in the galaxy, this is the Milky Way, and like an artist's impression of the Milky Way. And these are all the lovely spiral arms, and we're just right here, the sun. And then over here, this shows the kind of like local cloud. Or the local cloud. So the sun is here, and here are some of our nearest neighbors, like Alpha Centauri and Sirius. And so for these stars that have the kind of yellowy bit around them, we've actually got a measurement for their stellar wind. It's indirect, but we're able to tell how strong that wind is around those stars. And it actually varies. So we find that some of those stars have much bigger kind of cavities around them, and so they're better protected. And some of them have smaller, are kind of more compact and compressed, so they have less protection. And actually, it depends as well on how much material there is in the interstellar medium. So if you go, to a different part of the galaxy, and because the sun is kind of traveling through the galaxy, it will interact with different types of, the galaxy will be denser or less dense in different parts of it, and then that will change the size of the heliosphere. That bubble that surrounds us and protects us. So, how much the galaxy, or how much the sun and its wind is protecting us will actually change throughout its lifetime. So that's one type of particle. And the other type of particle that I'm interested in are called stellar energetic particles. So this is a picture of CERN again. So the sun itself is an accelerator, and it accelerates particles that we detect here on Earth. And so this kind of image here is really the solar wind, and then there's sort of particles on top of this. So this kind of interacts with the solar wind, interacts with the Earth's magnetic field and kind of compresses it. And some of these particles, then sometimes the sun also produces these very high energy particles that can get to Earth and sometimes reach the surface. So how they interact with the Earth is, first of all, the magnetic field of the Earth protects us and kind of blocks the particles, and it kind of mirrors them towards the pole. And so the solar wind, that's kind of the cause of the aurora. So that's more the solar wind, but when it gets funneled towards the poles, that's what causes the northern lights. So once the particle kind of hits the atmosphere, some of them get through the magnetic field, some of them are deflected. But if they get through, this is where they lead to the chemistry. So they can lead to the formation of prebiotic molecules. And it's kind of like a pinball machine. So when they hit the atmosphere, then they kind of go in all different directions and they kind of scatter. And they eventually, if they have enough energy when they start, they can reach the surface of the planet and maybe interact with the life that's there or help start it. So they lead to these particle showers. So they create, there's really rich chemistry that it already takes place in the Earth's atmosphere. So they just said there, the solar wind particles and also these high energy particles lead to the aurora, which you can see. So in fact, if you think about it, if the particles get absorbed as they go down through our atmosphere, so our atmosphere also protects us from these particles, it means if you go up into space, so if you're an astronaut, you get hit by more of these particles. So yeah, they're not great for you. So I just need to put that, like, politely. Maybe that's one of the links to the bow and the scary bit. If you're an astronaut, you're not particularly well protected. So the astronauts actually have like a dose rate. It's kind of like getting an X-ray done. That's kind of very mild, much milder. But yeah, so they have a kind of total dosage they're allowed to have within their career. So they can't just stay up there for years, or it's very bad for them because it does things to your DNA. Yeah, so going back now to this like origin of life on Earth. So it's kind of a loop really, because the more we know about life or where life might have started on Earth informs us about where we're going to start looking for life on other exoplanets. So it's kind of like an infinite loop, or we keep iterating to get closer. So as I mentioned already, there's this kind of like delivery of, you know, prebiotic molecules from asteroids or life from an asteroid, but then there's these other two scenarios. This is, I think, one of the older ones. So this is the warm little pond. So you need something like a hydrothermal vent. This, I think, is in, you know, Yellowstone. Oh, yeah, maybe it's Yosemite or Yellowstone in America. So here you had this kind of pool. So you're on the solid land, but then you have your pool. And this is maybe where you're able to, you know, it's like cooking or baking. You know, you have your ingredients and you need the heat, and then you can maybe create something that will eventually turn into a simple life form. Or the other one is hydrothermal vents in the deep sea. So this was kind of found more recently. You know, there was lots of life found around these things, and then suddenly realized maybe life could have started in this kind of environment, because you've got a lot of a very rich chemistry because of the volcanic material. So this is another scenario. So this is also relevant for the moons of Saturn and Jupiter. They have detected similar kind of vent-like things on those planets. So that's another place people like to think that life might have started. And then now, even interestingly, there's this funny little life forms that we've detected on Earth, which don't even need oxygen to survive. So this is one of the creatures that was detected or found in the Mediterranean. And it lives in really, really salty water that has no oxygen in it, it doesn't interact with the oxygen, and it's found to live there. And so these things, you know, this is one of the exotic things, you know, that once you start finding them, you're like, oh, well, maybe it doesn't have to be life as we know it. Yes, so I think and this is also actually the idea that life is actually anti-fragile. So even though these particles that I'm talking about might, you know, like I said, they might, you know, be bad for humans, but in reality, life is probably quite anti-fragile, which means that it's going to evolve in whatever circumstance it lives in. And so like this little creature has decided to be able to, you know, it evolved to be able to survive without oxygen. So maybe on other planets, things can survive under other very harsh environments. So we have to bear that in mind as well when we're trying to think of where life could form. So I've mentioned the solar wind already. And I've also sort of alluded to the fact that the sun is not always the same depending on its age. So this is a picture of the sun, and you have these lines which are like magnetic field of the sun. And here on the left is again kind of shows the kind of basically the sun when it's quiet is very much like a big large bar magnet. It's just got a simple magnetic field that wraps around like that. But then the sun has a cycle, and it goes from this kind of quiet stage to more active. And basically that means the magnetic field of the sun is kind of, you know, made up of more little small dipoles. And this also means that the wind that it drives is less sort of spherical. It's kind of more patchy, and it can be fast in certain regions and slower. And so this happens so the magnetic field actually flips. And then also during this, when it flips, but it kind of flips by tilting and it goes over. And during this phase, it goes through this kind of active phase. And this is actually also when the aurora are more visible, is when the sun is quite active, because it means it's like more likely to have like to flare, and it sends off like sort of large amounts of material that get fired straight at Earth. And so this is kind of to show you that this is what expands. All this kind of, this material here is the solar wind. This is what kind of expands out into our solar system, as I described before. So the sun in the past, though, was much more active. So it has a short-term cycle of, you know, 24 years, but it has a much longer, not cycle, but just trend. So younger stars are much more active than the sun is today. And this is actually one of these eruptions from the sun. So depending, they can hit Earth, and then they can knock out the satellites if they do that. And then sometimes they're kind of, you know, just fired off in other directions. And the sun would have had much more of these flares when it was young. So that means Earth would have been hit by these flares more when it was young, and that would impact the atmosphere. And in these flares, this is where the energetic particles come from. So then you should get more of these particles when the star is younger. And this is also just another cool aside. So there's we can actually use carbon dating to tell when the sun had these big flares in the past, because carbon dating is actually linked to cosmic rays, because the cosmic rays produce carbon-14 in the atmosphere of Earth, and then it goes into plants or us. And then, but once the thing is dead, the carbon-14 radioactivity decays, so you see less of it. So in the same way that you can use you can use these as carbon-14 in trees, can tell you when there was these really large, rare events up to thousands of years ago. We can tell when the Earth had one of these really large events that would have hit Earth, which I think is very cool. So this is the sort of overview of the kind of research that I look at. So I look at basically everything I've just talked, well, not everything I've talked about, certain aspects. So I look at these galactic cosmic rays and the stellar energetic particles to try and calculate how many would get to the surface or, in the vicinity of an exoplanet, because they can cause these prebiotic molecules that I've mentioned before. And I'm not just interested in these kind of habitable planets, but I'm also interested in things like Jupiter. And the reason I'd be interested in something like Jupiter for another in another system is because they're much bigger, so they're easier to observe. So we can kind of get more hints about the energetic particle environment of other stars by looking at these bigger planets. And we're also going to be able to detect more of bigger planets. So we'll get more information faster by looking. So basically, if we look at planets that we don't think are habitable, that will tell us something about the environment around habitable planets. So two of the systems that I look at that are very interesting, they're red dwarf systems, which I mentioned before. So these are kind of much cooler planets. And these are actually some of the top candidates in the search for life, which I'll actually tell you about in a second. But yeah, I look at this one called AUMIC and GJ436. GJ436 has actually been observed with the Hubble Space Telescope, and it has this cometary material behind it because it's so close to the star that the star is causing material to constantly be evaporated. So they can detect the signature of this comet behind the exoplanet as it goes around the star. And this is kind of old. It's roughly the same age as Earth. Whereas AUMIC is actually quite young. So it's this very harsh environment where the star is flaring all the time, very frequently, and the planet is orbiting quite close. So it's being exposed to a lot of these particles. And as I've mentioned, we basically think that young stars or active stars and M dwarfs are actually, or red dwarf stars are thought to be more active than the sun, which means they have all these flares. So they should produce more stellar energetic particles. So when we're thinking about life for other planets, we have to remember that different types of systems might have more of these particles, which will affect the chemistry and biology on the planet. So as I've already mentioned TRAPPIST-1, and this is where one of the planets that we're looking for life on another exoplanet. But as I've kind of mentioned, there's pros and cons to the different types of stars. But one of the reasons people are looking at red dwarf stars is because the exoplanets orbit close to the star. Planets in the habitable zone orbit close to the star. So that means if you're looking at the transit method, they're easy to detect because you've got your star, and your planet orbits around the star quite frequently because it's quite close. So that means in a relatively short amount of time, like 30 days, you'd be able to detect it going in front of the star. And then you can do that multiple times in a year. If you're looking for something like Earth, it does that once a year. So it takes you so long to find those exoplanets in the habitable zone. So it's more favorable. You'll find more habitable planets if you look at these red dwarf stars because the planets are closer. So this has been a huge sort of focus of all these planets that I've told you about, these thousands of planets. These are the real focus, is the red dwarf exoplanets in the habitable zone, because we can detect them quite easily. That's just a bias, a detection, like in our, the type of planet that's easy to detect. There's no reason why life should necessarily form on those planets. And in fact, so this, as it shows here, the star is kind of redder than the sun is. And so that means that they get, less of certain types of light and more of other types of light than the sun does, the sun gives to Earth. And this is important for things like, photosynthesis, and people look into this, whether or not you have enough UV light on these cooler planets or on these cooler stars. But as I've mentioned, these stars flare, red dwarf stars flare a lot, and also because the planet's closer, it means they're going to be hit by, you know, more of the material. Because if you're further away, like at Earth, the material has kind of time to spread out before it hits Earth. But when you're very close, you're more likely to get hit by one of these flares. And so basically young stars, sun-like stars, or red dwarf stars flare an awful lot, and can potentially wipe out life on a planet because of these very energetic events. And these have been detected a lot with these. So these two missions detect they're the transit method telescopes. So they do the blinking planets. But in the same way that that starlight dipping, you can also detect the starlight increasing. So these two telescopes have also looked and seen these flares. Now, so they don't get an image like this, but they just see the light bulb getting brighter as these flares erupt and hit the planet. And they've detected really, really massive flares for many of the stars. So, yep, very dangerous living around another star. And yeah, so I suppose what people, or like I like to think about sometimes, I just stole this from Wikipedia, that life began, you probably can't read this now, but life began about 4 billion years ago on Earth. So Earth is 4.6 billion years old around. And so you have to try and think about what was the sun like 4 billion years ago. It wasn't like it is now. So it flared a lot more. And so you have to kind of build that into your model of like, well, could life have started on Earth, or what were the conditions like when life started on Earth? And this is some of the stuff that I look into, is trying to model what the sun would have looked like really for billions of years ago, and then how many of these kind of flares the sun would have had, and then what would that do with the chemistry. So yeah, I just have a few more slides. And so finally, more towards the observations, which I don't do myself, but how are we looking for life on another exoplanet? And so this is a nice, confusing plot by someone called Victoria Meadows. And this is Earth here on the left. So, okay, if you think about it, yeah, if you don't know much about life, you do know that we use oxygen. So oxygen is pretty good signature of life on Earth, if you think about it, because we plants make it. So if you can, in Earth's atmosphere, you have O2, which we breathe, then you have O3, ozone, and you have water in the atmosphere. So these are all things, if you saw them, you could be like, you might think, okay, well, if I see them on another exoplanet, then maybe there's life there. So these are called biosignatures. These are how we will detect life on another exoplanet. We're not going to be able to like see a green alien waving at us, unfortunately. We're going to be looking for these chemicals in an atmosphere of an exoplanet. And these other ones here. So CO2, what we breathe out. I don't do any chemistry, so it's all very complicated for me. So the telescopes are going to look for these types of molecules. But what Victoria Meadows has shown here is that she has this kind of way of, you basically need to detect or not detect multiple. You can't just detect one of these. You need to detect, combinations of three. It's kind of like a guessing game in order to say that it actually is a habitable planet. So here, for instance, you could be a red dwarf planet, but you've lost your ocean, so that's bad. You've no water. So you have O2, so you might think there's life there. You have O3. But if you detect O4, this cannot be produced by life. This is produced by something that's not alive. This is just a chemical byproduct. So if you detect O4, you know it's not life. Again, here, if you don't detect, these are the negative ones. So if you detect this, no life. If you don't detect water, then also no life. And again, so she's come up with this kind of way. There's just so many ways, basically, that you can produce oxygen that's not actually life on an exoplanet. And this is kind of at the kind of, cutting edge of what research or what people are doing now, is trying to figure out these chemical pathways. So like, if you've got volcanoes, what do they produce? And to try and work out what combination of molecules you need to detect in the atmosphere of a planet to say there's probably life on that planet. So this is kind of where we're at. And so finally, just a nice plug for DIAS. So some of the instruments that DIAS are involved in on the left, hopefully you've all heard of JWST, the James Webb Space Telescope, which was launched last year. And so I and Tom we're both involved in this like mid-infrared disk survey. So this is looking at very young stars. So the material around the young star, this is the chemical like inventory of these stars. So whether they have the prebiotic molecules. And JWST is also what the instrument that's going, or the telescope that's going to look at TRAPPIST-1 to see if there's any signatures of life. So these molecules I just mentioned, like oxygen in the atmosphere of TRAPPIST-E, I think, or TRAPPIST-1F. And then, so JWST is kind of like a multifunctional instrument. It's going to look obviously at loads of different science projects. So in the future, an ESA mission called Ariel is going to be launched in a few years, which Tom and I are also involved in. And Ariel is dedicated to looking at exoplanet atmospheres. So it's going to be doing this exoplanet characterization. So it's going to detect all these different molecules. And again, Ariel won't be, and same with JWST actually, they won't be focusing on habitable planets or planets orbiting in the habitable zone. They'll probably do, you know, maybe 5 to 10 in total between them both, you know, and that's really pushing the capabilities of these instruments. Whereas Ariel, on the other hand, is going to look at like thousands of planets that look like Jupiter. So if we can use something about what we know the energetic particles will do to the chemistry in atmospheres around something like a Jupiter rather than an Earth-like planet, then we can use Ariel or JWST to help us figure out what the energetic particles are doing to the life on the planets. So back to the first slide. Do we think we're going to have Slimer or X-Men mutants on other exoplanets? We don't know yet. It's very complicated and complex. But what we do know, I suppose, is that very high fluxes of energetic particles are bad for life as we know it. And yet at the same time, they drive the formation of prebiotic molecules like HCN, hydrogen cyanide. And so we do know in small doses that they're, you know, they could have started life on Earth, and yet we know they could also wipe it out if there's too many of them. And so I think I will leave it there. And if anyone has any questions, I'm happy to answer them.
Thank you, Donna, for a very interesting and very accessible talk. So, yeah, questions, anybody? Everybody's convinced it's something like what's on the left, right? Yeah.
You mentioned the cosmic rays. I was just thinking of the Carrington event, you know, which was a big event that knocked out a lot of power cables way back in the 19th century. And I was reading more recently that there seems to have been another such event around the year 900, just looking at the tree rings. And as you said, carbon-14 is also in rock formations, and they're beginning to discover more and more of these big events. Do you think that they're all solar related, or do they come from another source?
I think that they could also come from other sources. So, but maybe on a longer timescales than the carbon dating would. The carbon dating goes back to maybe 50,000 years ago. So maybe anything in the carbon dating is probably the sun. And then on a longer timescale, if it's, you know, something like if a star exploded nearby us, that would also be imprinted somewhere. But I think we would have other evidence for that if something really, really big had happened in the last 50,000 years, as far as that would be my guess. Yeah.
There has been a claim of enormous iron isotopes,
which might be related to a nearby supernova event in deep ocean cores. And beryllium-10, of course, is the other tracer for this sort of event. I mean, I think the lesson is that things can get pretty nasty out there occasionally. So, yeah.
Yeah.
Thanks, Donna, for a great talk. You mentioned, go back to your diagram that you had of the different types of cosmic particles, and what CERN detects, and then what's extragalactic, etc. And you made a passing reference to that there's infrastructures or systems being developed to detect these. So obviously you've mentioned some of the space-based infrastructures, aerial, James Webb Space Telescope, all of which DICE are involved in. But are there other ground-based mechanisms for detecting these types of particles? I think I'm aware of, for example, one large infrastructure under ice, or there's some other infrastructure, look, I can't remember the name of it, actually under, that they're trying to put under the ocean to detect things. So can you say a little bit maybe about what other, besides the space-based infrastructures, what other ground-based type infrastructures have been put in place to try and detect these particles?
So
Great.
so the telescopes would detect kind of like the indirect chemical tracers of the particles, and then on Earth we can detect the actual particle, or a more direct evidence of the particles themselves on Earth. So some of the ones that DICE are involved in is the HESS, the Cherenkov telescope arrays. So as the particles go through the atmosphere, they give off light, and you can kind of, it's actually very similar to CERN, that they can kind of trace back. They look at the particle showers and they can trace back what the initial energy of the particle was in the accelerator. So it's the same in the atmosphere when they detect the kind of light and like secondary particles that got produced at the bottom of the atmosphere. Then they can trace back what the energy of the cosmic ray was at the top of the atmosphere. So the Cherenkov telescope array, which is coming up soon, that's being built. Then there's HESS in Namibia, which Robert actually works on as well. And then there's also this gamma ray detector. So that's like a higher energy than, they're actually in space though, again, sorry. The gamma ray detectors can detect gamma rays come from the cosmic rays. So they can also tell us about the cosmic rays from the galaxy. And the other ones, what are the other ones? There's Pamela's, I think that's space. Ice Cube. I couldn't remember the one. Yeah, Ice Cube. Yeah. Ice Cube is the one with the ice. Yes. And I don't know actually about the one that you were mentioning about the underwater, but I'm not, my expertise wouldn't be on the KM3 net. Yeah. There's a few, and yeah, there's a few up, there's always, what's good about astronomy, there's always new instruments coming up. Yeah.
Okay, thanks.
Yeah.
Okay. Actually, when I was sitting there, I was thinking about, your point about cosmic rays being important, perhaps as a driver of chemistry, which might ultimately lead to life. But then if you have too much cosmic rays, that could be a bad thing. But one thing you didn't mention, and perhaps we don't know enough about it, is the effects of cosmic rays on DNA and causing mutations, evolution, because evolution is also important as well. And what I certainly don't know about is, if you have, well, Eukarya comes from Donegal, and there's a lot of radioactivity in Donegal, right? And so you have also stuff coming from the ground, what dominates in terms of evolution? I'm not sure.
Yeah, on the surface of the Earth at the moment in present day conditions, you actually get more radiation from other sources of the surface of the Earth at Earth. So the cosmic rays are actually giving you less than other radioactive sources like in the Earth would be giving you. Yeah, sure. But that's for now. But yeah, where I mean, I'm not sure that there's that they do many experiments on people with the radiation.
No, not people.
No, I know. But they're things.
I just meant in terms of
they do expose like bacteria to radiation. Yeah,
it does cause mutations.
Yeah, it does.
I just wonder whether for life to evolve, very simple things.
Yeah.
They may also be good in that regard. in the correct dose.
Yes, yeah. No, absolutely. Yeah, no, that is part. Yeah, that's the other kind of side to it. And there's also like hints that that, you know, the DNA helix kind of spirals in a particular direction, and that there are hints that the direction that it spirals in is due to the cosmic rays themselves as well, because that comes from how they something to do with how they go through the atmosphere leads to that. Yeah. But I like the more space-based research and less on the mice. Yeah.
So, any more questions? No, great. Well, can I just thank you, as I say, for a very interesting and very accessible talk, and we're delighted also to have you back in Dice. Thank you.
Thanks.